Hello guys, welcome to Tux Riders and the FreeFEM series. To continue our discussion about FreeFEM, in this video we want to discuss some of the features of FreeFEM for performing adaptive meshing. Let's go for it. So similar to the previous videos, we have a couple of examples here, and I go through them one by one. They're focused on adaptive meshing, features that FreeFEM has built in, which are provided by some interfaces to a couple of mesh manipulation libraries. So the first example is related to the most basic form of mesh adaptation that we can perform. In this case, we have like a square mesh, and then we define a finite element space on top of it. Then we define u, and u equals to a function here. So something like this. But there is one difference, and one difference here in comparison to a normal function, and that's actually this operator showing that this is actually a function with the output of true and false, or 0 and 1. So for u, when we plot it, you will see that u is actually like the 1 for regions that are inside the circle with the radius of the square root of 0.5 and 0 elsewhere. And that's actually the thing that we need to pass to adaptmesh to adapt the mesh, the provided mesh. In this case, this is mesh variable that we have created according to u. And then you will see what happens. And then we can define a couple of other parameters that you can see some of them in other examples. And then we plot the mesh. So let's run this exciting example, and then you see how simple it is to perform mesh adaptation in FreeFEM. So we have example 1. I turn off verbosity. So this is the mesh, the original mesh. Then I press enter. We have 3 plot statements here with weight equals 1. So I need to press enter to go through them. So this is the mesh, and then this is u. I press V to display the values. You can see that the 1 inside the circle with the radius of 0.5, because we have here the square root of this, and then it means that we have already eliminated the power of 2 here. So the radius is 0.5, and then this is actually u. And then when I press, you see that if I press M, the mesh is still like the original mesh. But when I press enter, now we see the adapted mesh, which is based on the provided value of u. So it is refined on the interface, and then as you go further from the interface, it becomes coarser. So this is actually the very nice interface available in FreeFEM, that you can adapt any kind of mesh according to the metric you provide, or a criterion, let's say. In this case, it is u. So that was the first example. Let's go to the second one. The second example is very similar. We still use adaptmesh, but in this case we are going to have like another shape for that. For instead of having circle, we define another function. In this case it is box, so everything else is the same. But here we have box that defines actually square. So as you can see, this is still a function that has a binary output, 0 or 1, and then we define the boundaries inside this domain, inside this these parameters, this parametric definition. Let's say we have 1, and outside we have 0. Then we define a function, finite element space. In this case it is phi. The name of the function is phi, which is just resembling the level set method. We discuss these things later in another video. And then we define a phi like box minus this is because it is 0 and 1, and this is something that is not necessary. As I said, this is for level set method, but when we reduce 0.5 of it, then it becomes something negative and positive. So positive and negative, and then with that adapt the mesh, and then we adapt the mesh based on that. And as you can see, there are other parameters that we can provide it with, like at the maximum size, minimum size, and also the error, which is very important. They're defined here. And then you can play with this parameter to see what happens to the output mesh. So I run the example 2. This is the original mesh, and this is the mesh after performing the adaptation. So you can see that how simple it is to create this kind of stuff in FreeFEM. Then we can have also more complex shapes in example 3. So I close these 2 examples. In example 3, we have like a binary shape. In this case, it means that a combination of 2 shapes that we have defined parametrically. And then you see that we have a circle, box. First we define a mesh, and then we have these 2 functions that are stored in temp1 and temp2. There are various ways that we can do this. In previous videos, you saw also a couple of other ones that are, it is just for combining the fields, let's say. And in this case, we say maximum because we just, the adapt mesh perform things based on the 0 value of the criterion, of the provided criterion. So in this case, we say max, and then these 2 shapes are combined, and then we adapt the mesh based on the provided field, let's say. So I run example 3, and then this is the mesh. As you can see, this is very fine because I want to have the I want to have a smooth shape being captured by it, and then when we want to perform the adaptation, it yields to a smoother shape. So this is actually the second output. So plot U on it. So these are the values. You can see that they are from 0 to 1. And then I press enter, and this is the adapted mesh, which is very fine on the interface, which is something very useful for, let's say, like simulations that need some refined mesh on the interface. Later on in Talks Riders, we will discuss a couple of moving boundary problems, and on those kind of problems, this is a mesh that is highly desired. Another example can be like create a simple screw, 2D screw. In this case, it is very similar to the previous example, but we combine more shapes. So it is like this. You can also write this in one line. So we have 3 different functions combined into one single variable phi, and then we pass phi to adapt mesh with some parameters that we have defined here. And then we see what happens. So again, we have, this time we have 2 plots, one for the phi and one for the mesh. Let's see how it works. So this is very similar. These are just examples, different examples of what we can do with this. So this is actually the screw in 2D. If I press M, you can see the mesh. So in these regions, it is not very smooth because the original mesh is coarse. And then I press enter, and I have this very nice mesh generated adaptively. So these are the things that you can do with that adapt mesh function. And then because this is actually a finite element space function, let's say, it means that it can be also a solution of a PDE, and it means that you can adapt a mesh based on a solution of an equation. And this is what example 5 tries to do. So in this case, we have a mesh which is defined using a parametric definition of the geometry, which is a kind of L shape, let's say, geometry. We have already discussed these kind of things in the mesh generation video. And then we want to solve the Poisson equation on it, like a very simple stationary diffusion. And then we have some boundary conditions. What we do, because you know that with adapt mesh, we had the error. So the error that is used for adapting the mesh, and it can, the lower error leads to finer mesh. And in this case, what we do, we solve the equation, we solve the Poisson PDE. The solution is stored in U. And then we adapt the mesh based on this U. And it occurs in a loop 6 times, and each time we make the error half, so we divide it by 2, and then we compute this again. So because we plotted in each iteration, we should be able to see how the mesh evolves. So I run example 5. This is the original mesh, a very coarse mesh. And we have, I think, I should be able to plot the values as well. So I press F for filling and value. No, this is the original mesh. And yeah, this is actually the solution of the Poisson equation. So I press F to have the fill. And then over time, also M to display the mesh. And over time, we have like the mesh being adapted according to the solution of the equation. So this is the evolution of the solution, and this is the mesh being adapted along with it. And yeah, so you can see that now we have like a very nice and smooth solution, while we started with a very coarse mesh, let's say, and now the mesh is adapted to the finite element function. In this case, it is u. So yeah, this is a very useful feature when we want to deal with more complex PDE. So instead of having like a fine mesh, we can have like this kind of mesh adaptation to save a lot of time during the simulation. So these examples were for 2D so far, and now we have some examples in 3D. In 3D, we do not have the adaptmesh function, so FreeFEM doesn't have any built-in support for 3D mesh adaptation, but instead it has some interfaces to, as I said, to a couple of external mesh manipulators. So in this case, the first example is related to Tetgen. We have already discussed this in the 3D mesh generation, and I told you that we will discuss it more in the mesh adaptation video, so in this one. And in this case, this is very similar. So you need a metric, and you pass it to a function that adapt the mesh, but in this case, the only difference is you need to compute the metric. You cannot pass it as a finite element space, because this is Tetgen, and it needs a kind of metric that can be calculated using meshmet. So we also need meshmet, another external tool that has a nice interface in FreeFEM. So we generate the mesh, we have the function to describe, like the circle. In this case, it is a 3D circle, so a kind of sphere. And then we have a finite element space defined on it, and then we reduce it by 0.5. This is, as I said, a typical level set definition for things. And then we pass this u to meshmet, and then it computes a criterion, the metric for us. It has also some functions, so for the minimum, maximum size and error, this time we have it already built into our metric. And then we pass this metric to Tetgen reconstruct with some of the parameters, some of the, let's say, flags that Tetgen needs for performing the mesh adaptation. And then the size of volumes are like the size of one tetrahedral according to the metric. And then we have, like, we need to, this is something we discussed in the first video, u equals u means that interpolate the original u onto the new mesh. And then we plot it using medit. So let's run this one. In this case, we have example 6, sorry. And yeah, this is a typical output of Tetgen. When you have Tetgen in the code, this is what happens when you have like the scene being rendered, and also being this is for rendering, and then we pass it to the reconstruct. So when I close this, this is the original mesh, and when I close this, then it starts to perform the reconstruction. And then here is the adapted case. So I press F1 and then I can have like a clip on a mesh. So this is the way that Tetgen works. Personally, I do not like the output of Tetgen, but you can also have a lot of control on various aspects of it. So I press F2, we can see that we can change the clip plane, and yeah, this is the type of let's say adaptation that Tetgen does. So a better mesh manipulation library is actually Mmg. This is very advanced, and that's what example 7 tries to demonstrate. In this case, you can see that how simple it is to work with this. No metric is required. You can directly pass the finite element space a variable to that. For this case, we have a sphere, again, like defined in 3D. And we map it to a cube mesh, and then we call very similar to adaptmesh in 2D. In this case, we call it with Mmg 3D mesh, and we provide it with the metric. And then we plot it with Medit, and you will see that how simple it is and how nice it is in comparison to the output of Tetgen. And that's why I said that I do not like the Tetgen mesh manipulation. In this case, Mmg is more sophisticated. So let's run example 7 together, and you see how nice it is. So this is a very typical output of Mmg. People work with it. People who work with it know it. And then after having the adaptation, you see that the mesh has become non-structured. I press F1, and this is, as you can see, very similar to adaptmesh. So you have some gradient here for the sizes, and then the minimum size and maximum size are sort of interpolated, and a very nice mesh is generated. So generally speaking, most of the times I recommend people to use Mmg instead of Tetgen. So yeah, and then the last example is very similar to what we had for the solution, but in this case it is in 3D, and we use we have Mmg3, but with a metric produced with meshmet. So this is actually a combination of these 3 examples. So we have the metric that is calculated on the solution of a PDE. In this case, that's again a Poisson equation with some boundary conditions. And then because this is a bit complicated, we have also, the results being written on a VTK file, so we can visualize them using ParaView to have a better visualization. This is something that we will discuss in the next video. So in this loop, what we do is actually we have 4 iterations. We solve the equation, the solution is stored in U, and then we have like some variables defined for rescaling. This is not something we want to deal with, but in the end, we have the meshmet being performed on U, and we pass meshmet to the metric calculated by meshmet to Mmg3D. Here you can see that we have also all those parameters that you typically have in Mmg code. Those parameters are available here, and you can modify them. And the mesh that we use for this is actually a cube that has like 1/8 of it truncated, and this is very similar to the 2D case. So in 2D that was L-shaped, and in this case you will see how it looks. So let's run example 8 together, which takes a bit longer because it needs to solve the equation and adapt the mesh 4 times. And yeah, so these are the output of Mmg, 4 times performed on a solution of the problem. And then we have the solution stored here for us. So what I need to do is calling ParaView and running it. And then I open this the group of these results that are actually grouped into one. So I can have them like a time series, but each time point actually corresponds to 1 iteration. I press apply, so this is the mesh, as I told you, 1/8 of it truncated. This is the mesh So, and this is U actually. Let's go to the next time points, and you can see the mesh being adapted according to the solution that we have. If it's difficult to see, maybe. So like this. So as you can see, the mesh, Mmg 3D and mesh adaptation in 3D work like this. And this is quite powerful and very efficient. So yeah, these were the examples that I wanted to discuss in this video. I hope you find them useful. Make sure to grab the codes and run them yourself. You can find a link in the description to the GitHub repository containing these codes. See you in next videos. Bye.